Yeah, my name is Andrey Lokhov. I'm with Theoretical Division in Los Alamos National Lab. I'll tell you about the detection of cyber-physical faults and intrusions from physical correlations. So in this talk, we'll apply the outlier detection communities, which is the main topic of this workshop, to the protection of cyber-physical systems. And those are physical networks which are governed by the laws of physics, but regulated by a control system coupled with a computer network, which may exchange information with the physical part of the system in order to apply optimization or control of this one. And the examples include, for example, smart power grids, avionics, all sorts of critical civil infrastructures and autonomous control systems. So basically there is a constant feedback between the physical part, the measurement from sensors, and the control from the cyber part, which comes from the analysis of the data. However, this interdependence of these two parts can create basically a vulnerability for the system, because an attacker or, for example, intrusion or measure fault in the control system can create a significant damage or degrade the performance of the physical system itself. And the question is, and of course it is natural to expect that the intrusions or faults which occur in control system will leave signatures, and we can track them as anomalies in the physical part. And the question is, can we basically use the measurements of physical signals of sensors in the physical part to detect the intrusion and to localize, to localize it? In the example which was given by Jeff in today's first talk, for example, if we have a self-driven vehicle, and the question is, so for example, if the control system, the cyber system of this vehicle is attacked and affects some physical parts, can we, for example, measure, let's say, speed, acceleration, fuel consumption, and based on these physical quantities, detect that something bad is going on and develop a response? So the general setting, once again, is to use the sensor measurements from the physical part and try to detect and localize failures and intrusions in the whole system. Of course, one can, for example, apply the outlier detection to the individual signals, and this is a well-studied area, and this can be a signature of a crude attack or of a significant failure. But however, in the examples of more sophisticated coordinated scenarios, it is important. So basically, we might not see the outliers in individual signals, and thus we have to explore the spatial-temporal correlations. And so our goal will be to develop a protocol and the set of algorithms, which would be, well, of course, all these words, which we always want from all the algorithms, so which will be scalable, so operating a large number of signals, general, meaning that it can operate on the signals of diverse nature, robustness, if there is a significant portion of noise or the signals are incomplete, and then low complexity to allow a deployment in online fashion. And so this will be the path for the solution that we'll follow. So basically, first we'll detrend the signals and construct the appropriate correlation metrics. And then mathematically, the problem will be to work with these correlation metrics and to develop a method for detecting the presence of the anomaly, to localize the anomalous device, and then use the take data to identify what is the cause of the anomaly. So a more precise definition, we assume that we observe n heterogeneous time series, so time streams. And we assume that these signals can be decomposed in three parts. The first part is the trace, so basically the normal behavior of the system. So then uncorrelated noise, and if the attack or failure is present, then there will be the third part, so the signature of this attack, which will also affect the signal. So in this example, and then basically the observation is that if we work with the residuals, so if we subtract from these signals the trace, so the normal operation, then this will be uncorrelated if the attack is not present, and this will be correlated if something bad is happening. So in this example, if we have, like, for example, in blue a signal, we subtract the normal behavior, we get something, so that will be the residuals we will work with. Unfortunately, this trace is unknown, so of course one can, for example, try to learn it from a series of normal operations. But so basically in the examples, we can do many sophisticated schemes to how to approximate this trace. We'll use very simple example. We'll just detrain the signal by applying the Rollin mean. So basically, by averaging the fluctuations over a certain time period for each point t, and we'll test the correlations between the residuals. So in this, for example, here are 3 examples where, for example, these two, the bottom 2 signals, they witness an appearance of an attack at approximately 11. But basically, so individually, it's probably hard to track some outliers, but there will be some correlations between them. So given these residuals, we construct the correlation matrix, which is basically simply a Pearson correlation over a certain time window, sliding time window over a certain time. And then again, the assumption is that under normal operations, so if there is no value, then the expected value should be 0, so the value should fluctuate around 0. And in the presence of attacker value, which have the same behavior, the expected value of the corresponding element of the correlation matrix will be non-zero. And so we are basically here. So we construct the correlation matrix, and now we'll work with this. And the goal will be basically, first of all, to detect if the anomalous submatrix is present. So basically the matrix where these high elevated values are present. And so here we use, this is something which is close to what is done, for example, for detecting single community in graphs. So the claim here is that we can detect the presence of anomalous submatrix by monitoring the spectral gap. The spectral gap is the distance between the first eigenvalue and the second eigenvalue, largest eigenvalues. And basically, the claim is that if the anomalous submatrix is present, then the spectral gap will be, the distance between the first and the second eigenvalue will be much larger than all the subsequent distances, in the case where the signal is sufficiently strong. So the intuition for this is, for example, coming from the study of rigorous study of simple systems in the ideal case. So for example, consider here the rank 1 matrix with normalized U, which is basically theta U transpose, with theta is the strength of our signal, corrupted by a Gaussian Wigner noise, which takes the form of the Wigner matrix. Again, standard and normalized. So it is a well-known fact that the spectrum of this noise will take a form of a Wigner-Somerset law with the support from -2 to 2, and then in this system there is an emergence of the let's say phase transition type behavior. So if theta is larger than 1, there is a clear gap separating the largest eigenvalue from the bulk of other noisy eigenvalues, and if theta is less or equal to 1. This largest eigenvalue enters the bulk, so there is no gap, and the corresponding eigenvector doesn't contain any information on the signal itself. But how do we do? So this is a system where, for example, we know we have assumption on the form of the noise, on the matrix, etc. So how do we do in the real situation? And so we suggest the following criterion. So since our assumption is that there is possibly a present anomalous matrix, anomalous submatrix, and so this first spectral gap is due to this, and all the other values of the eigenvalues are entirely due to noise, we can try to estimate the characteristic noise scale by basically playing with the variances given by these eigenvalues from the second to the last, and estimate the characteristic noise scale. And then our detection criterion will be if the spectral gap between the first and the second eigenvalue is greater than the second gap plus delta, this characteristic scale, then it means that the anomalous submetric is present. And now we have to localize it. So for the localization task, we used several algorithms. So basically, let me tell you the two main ones. The first one was based on the low-rank approximation, and the second one is based on the biclustering methods. So low-rank approximation is as follows. So we can make an assumption that our matrix looks as follows. So for example, here, let's say we have that node 1 and node 4 are anomalous, and so have a higher correlated value. And so we assume that basically our matrix has this form corrupted by some noise. And then the idea is to search for a rank 1 matrix which will approximate in the best way our correlation matrix M. So this solution to this problem is well known. It's super easy. So we'll just apply a single vector decomposition, and we retain the largest eigenvalue and the corresponding eigenvector. And this is our solution. Unfortunately, this eigenvector, in general, it will contain all of the elements of this vector will be non-zero. So it doesn't give us information on what are the nodes which are anomalous. So we have to apply something else, which is sometimes referred in the literature as Sparse Pca, meaning that we want to approximate it with the vector which has only at most k non-zero components. And in general, it's an NP-hard problem to find such Q, but not in the case of rank 1. In the case of rank 1, you can prove that it's, again, super easy. You simply sort all the elements in this vector Q and you threshold, and you leave only the k largest eigenvalues, and this give you the location of the anomalous submatrix. But unfortunately, again, with real data, we don't know what is the size a priori of the anomalous submatrix we're looking for. So how do we do? Usually people, so there is a classical method of dealing with this, which is called, let's say, like elbow diagram method. Basically, if we monitor, we can scan through different values of k and monitor the error which we are doing on our prediction, and then we can hope that, for example, the elbow will look like this. So at some point, there will be a k star, critical k star, which will capture all the information, and then the error won't improve much, and that's what we will take as a size. Unfortunately, in real world, the elbow can look like this, and then there is no way to understand what is k star. So our suggestion was to basically always take k star of order of square root of n. And here's the reasoning for this choice. The reason is that probably we don't want to detect all possible devices which are anomalies, but we want to be sure to detect some portion of it, which is significantly large, which will allow us to identify the cause of the failure of the attack. At the same time, the square root of n is a practically achievable bound on like the smallest community, which is currently achievable by submatrix detection algorithms in ideal cases, for example, with Gaussian noise or et cetera, et cetera. So basically, our recipe will be to take to search for the submatrix of the size square root of n. So I described one algorithm, which was based on the low rank assumption. Now, actually, we also tested an algorithm which doesn't make this assumption. So it's a biclustering method, which is often used in biology, for example. And the idea is just to say that we'll be searching for a submatrix of size k by k with a high elevated mean by some greedy algorithms, basically by permuting rows and columns and restarting several times and trying to find the best local optima. And we test two algorithms like this. One classical one, which is very used right now in many fields, and a very recent improvement to this with some performance guarantees. And we use some L-Worms terms, and again, our strategy will be to use the square root of n value for the k. So we are basically here. So I described this localization of anomalous devices. Then once we localize the metrics, the idea is to use the take data and to see what these nodes have in common, and this will probably give an indication about what is the failure of the cause. So first of all, we just, of course, we started by looking at the synthetic data just to make sure that everything works. So for example, here we generated just 900 random walks, 50 among them correlated, and then so the spectrum looks like this in the semi-log scale. So there is a clear pronounced gap. So our detection criterion triggers the detection. And then if we localize with this recipe of localizing 30, all correlated signals are correctly identified. And if we look at the ground truth, there is 5 mistakes by Sparse Pca and 1 by big clustering, but at the same time it requires quite a large number of warm starts, which is undesirable if we want to do the following. So basically we applied this to some real data, which was an air conditioning system in a large building in the national lab with 1,000 heterogeneous data string samples sampled once per minute. And so our example was given by anomalous behavior of one of the fans in this system, which was starting to oscillate. And the idea was, can we, for example, so this was our first testing example. And indeed, we found that the application of the described protocol in the case where the anomalous signals are included was triggering a good detection and the perfect localization of the sensors. And finally, we have performed some controlled experiments by playing with the set points related to 16 sensors, and basically as a function of n total stream considered. And the idea was that we are able to perfectly identify the anomalous sensors if n is, let's say, so there is a failure in the localization performance if n becomes very large. So basically, here there is a phase transition type behavior around square root of n, which basically validates our assumption. Now, if we're not interested in perfect identification, then, for example, if we're interested only detecting half of the sensors, then everything works fine for general n. So here I describe the protocol for identification of anomalous sensors, and we're planning to do some more experiments with real system, and to explore the inclusion of communication data from the cyber part. Thank you.
So we have time for a couple of questions.
So are you analyzing the signal? Is a control signal or the cyber signal?
So basically, we are so for example, in this test case of air conditioning system, we were measuring temperatures, like real temperature fluctuation, valve opening positions, and air flows. So these are real heterogeneous physical signals which can be continuous or discrete, etc. So that's why the first challenge was to construct a correlation matrix which will take into account all these heterogeneities and then apply all the schema described, and to understand if we can, for example, if we can detect and localize the subset of these temperature sensors, of these physical sensors, we belong to the anomalous, let's say, part of the system, which was fan 6 in this example.
That is true, but in most industry, all the sensor data is collected through the SCADA systems, and the SCADA systems is eventually transmitting back to the control center, wherever that is. So if you are collecting the data, I mean, the control center has the main place where the data is collected, and that's where this signal needs to be analyzed. However, once the data is collected through the SCADA system, that data is put in the SCADA protocol. So you won't be able to recognize whether the temperature has gone up or temperature has gone down, because in this system itself, SCADA protocol, it will tell you that, okay, the temperature has gone to 50 degree or temperature has gone to 10 degree.
So basically, we were using real systems, so we were doing real experiments, and so that's how we were collecting data. So there is a control part, but there is also a historian which stores the values of the physical signals, or you can extract them in real time, and that's how we were doing and how we were obtaining the signals which had form like this. So this was our working material. So the main message here was, can we, based on these measurements of physical signals, detect that something wrong is happening in the whole cyber physical system?
Right. Are you also using SCADA systems?
Scalar?
SCADA is the control system which is used by most of the water, power, electricity companies.
I don't think so. But I cannot tell you what was the particular system it was in. So.
Any quick questions or yeah? Oh,
I think what I hear you pointing out is that you can measure things very directly, but what you've got is a set of indirect measures that would not necessarily be affected by an invasion and could detect such a thing as a secondary effect. Is that what you were trying to do?
So the idea is that, for example, if you don't have access to messages, let's say to information in the cyber part, or you suspect that this information can be corrupted, the question is, can you just, for example, leveraging this interdependence of cyber part and physical part, can you really work with measures that have nothing to do with the cyber signals, control signals, real measurements of temperature, et cetera, physical quantities, and to understand if something is going on, if there is a signature, if there is a quick signature of an attack. So that's the main message here. And of course, to make a reliable detection and to develop a protection protocol, you should probably at some point couple it with the information from the cyber part.
Yeah, essentially creating defense in depth.
Exactly, yes.
all right. Thank you. We can take all further discussions offline. So thank you. Here's the next presenter.